Space is supposed to be predictable. Objects drift, orbits bend, gravity rules. We calculate trajectories years in advance, tracking comets and asteroids with the kind of precision that makes the universe feel safe, knowable. But on October 1st, 2025, something changed. It started quietly, no press conference, no announcement, just a file upload to a secure server used by the China National Space Administration. A handful of images, metadata attached, timestamps, coordinates, instrument readings. Within 2 hours, those images were in the hands of astronomers across 3 continents, and within 4 hours, the world stopped pretending everything was normal. Because China had done something nobody saw coming. They'd gotten close to 3-eye Atlas, not telescope close, not observed from millions of miles away close. Close. The kind of close that requires a spacecraft, a rendezvous, a mission planned years in advance and kept completely impossibly secret. And the images they brought back, they showed something that shouldn't exist. Let's rewind for a second. 3-eye Atlas, the object with the name that sounds more like a password than a visitor from another star, had been on astronomers' radars since early 2025. Interstellar, hyperbolic trajectory, moving through our solar system like it was just passing through, no intention of staying. People were interested, sure, but not alarmed. After Oumuamua in 2017 and Borisov in 2019, the idea of interstellar visitors wasn't shocking anymore. Strange, yes. Exciting, absolutely. But by 2025, we'd come to expect that every few years, something from beyond our neighborhood would drift through. 3-eye Atlas was supposed to be just another one of those. A comet, maybe, or an asteroid. Something icy and ancient, shaped by forces we'd never fully understand but could comfortably categorize. The early observations supported that. Faint, distant, moving fast. Nothing too weird. Until October. Until China said, actually, we've been watching it a lot closer than you think. The images appeared first in a shared database used by the International Astronomical Union. No fanfare. No official statement from Beijing. Just there. Uploaded at 0347 UTC. File name, Atlas 3I. Proximal imagings at 001 TAR. At first, only a few people noticed. A research assistant in Geneva, a graduate student in Pasadena, a telescope operator in Chile who happened to refresh the wrong page at the right time. But once they opened the files, the word spread like wildfire. By sunrise in California, every major observatory on Earth had someone staring at those images. By noon, group chats were exploding. Emails were flying. Slack channels that hadn't been active in months suddenly had hundreds of messages, and the question on everyone's mind was the same. How? How did China do this? How did they launch a probe capable of intercepting an interstellar object without anyone noticing? How did they plan a trajectory, execute a rendezvous, and capture images this detailed in total silence? Because this wasn't a flyby. This wasn't some lucky long-range snapshot. These were close-ups. The kind of resolution you only get when you're right there. Meters away, maybe less. The kind of images that take time, precision, intent, and no one, not NASA, not ESA, not JAXA, not any space agency on record, knew China had launched anything capable of this. Let's talk about what the images actually show, because that's where things get uncomfortable. The first frame is a wide shot. 3-eye Atlas suspended against the black. No stars in the background. The exposure is too tight, focused entirely on the object itself. It's small, maybe 400 meters across at its widest point. Oblong, slightly irregular in shape, but not chaotic. Not the tumbling, jagged mess you'd expect from a comet nucleus or a rogue asteroid. It's controlled, deliberate. The surface is dark. Reflectivity is low, just like the early spectroscopy suggested. But it's not uniform. There are sections that catch the light differently. Patches that seem smoother, others that are textured, almost ribbed. At first glance you might think, okay, that's geology. Ice mixed with rock. Layers exposed by sublimation. Natural processes over millions of years. But then you zoom in, and that explanation starts to fall apart. In the second image, the camera is closer. Much closer. Now you can see the surface in detail. And it's not what a comet should look like. Comets are messy, chaotic, shaped by impacts, by outgassing, by the slow grind of time and temperature. You expect craters, cracks, boulders scattered across the surface, dust, randomness. But 3-eye Atlas, it's clean, too clean. There are sections, entire regions actually, where the surface is geometrically smooth, not polished exactly, but flat, even, like it's been shaped. And then there are the grooves, parallel lines running across the surface in near perfect alignment, straight, evenly spaced, Some shallow, some deep, cutting into the material like channels carved by intention rather than chance. In one section, the grooves converge at a central depression, rectangular, sharp-edged, measuring roughly 12 meters by 8 meters, based on shadow analysis and scale references. It looks like a panel, or a hatch, or a door that's been closed for a very, very long time. The third image is a thermal overlay. This one hits different, because temperature tells you how something behaves, not just what it looks like. When a comet approaches the sun, solar heating drives sublimation. Ice turns to gas. The surface warms unevenly depending on composition, angle, and rotation. You get hot spots, cold spots, variation. But 3i Atlas, the thermal map, shows something else. Sections of the surface are warmer than they should be. Not by much, just a few degrees Kelvin, but enough to notice, enough to raise questions. And these warm spots, they don't line up with the sun. They're not on the side-facing solar radiation. They're scattered across the surface, localized, clustered near those grooves, near the rectangular depression, as if something underneath is generating heat. And then there are the cold zones, areas that stay frozen even at perihelion, even when solar flux should be driving sublimation, as if they're insulated, protected, shielded by something that doesn't sublimate. This isn't how ice and rock behave. This is how engineered materials behave. By the evening of October 1st, the images had leaked. Not officially. Not through press releases or peer-reviewed papers, but through Reddit, through Twitter, through Discord servers and WhatsApp groups in every corner of the internet where people who care about space tend to gather. Someone, no one knows who, downloaded the files from the IAU database and posted them publicly. Within an hour, they'd been downloaded 50,000 times. Within 6 hours, over 1 million. In the reaction, disbelief, excitement, confusion, fear, comment sections filled with people saying the images had to be fake, CGI, a hoax. Others said they were real but misinterpreted, pareidolia, our brains seeing patterns where none exist. But the people who knew, the scientists, the engineers, the ones who'd spent their lives studying comets and asteroids and the way natural objects form, they weren't saying much. They were quiet. Because they were looking at those grooves, those flat surfaces, those thermal patterns, and they couldn't explain them. Late that night, a Slack message appeared in a private channel used by planetary scientists. Just one line. Has anyone run geometric analysis on the grooves yet? Within minutes, someone responded, yes. Aspect ratios are consistent. Angular deviation less than 0.5 degrees over 200 meters. That doesn't happen naturally. Another message. What about the thermal zones? Any models that fit? Reply. No. Sublimation doesn't explain it. Radioactive decay doesn't explain it. Internal heat from formation would have dissipated billions of years ago. Silence for 3 minutes. Then, so what does explain it? No one answered, because the answer, the one nobody wanted to say out loud yet, was too big, too impossible, too real. By October 2nd, space agencies were scrambling. NASA held an emergency teleconference. ESA pulled astronomers from ongoing projects. JAXA requested all available data on 3i Atlas from international partners. And China? Silence. No press conference. No statement. No confirmation that the images were even real, let alone that they'd come from a classified mission. Just nothing. Which made people wonder, why release the images at all? If this was a state secret, a probe launched in 2023, a rendezvous kept off the books, a mission nobody was supposed to know about, why upload the data to a public server? Was it a leak, a mistake, or was it intentional? A message, a warning, a way of saying, we saw it, we were there, and now you need to see it too. Because here's the thing, 3i Atlas isn't slowing down, it's not stopping. It passed perihelion in early October and now it's heading outward, past Mars, past the asteroid belt, back toward interstellar space. In a few months it'll be too far to study, too faint to track. And if China hadn't released those images, we'd never have known. We'd have watched it leave, called it a comet, moved on. But now? Now we're staring at photographs of an object that doesn't look like anything nature should produce. Smooth surfaces, geometric grooves, thermal anomalies, patterns that repeat, alignments that hold, and the question, the one that's been spreading quietly through research channels, through universities, through observatories on every continent, is this, what if 3i Atlas isn't a comet? What if it's something else? Something we don't have a name for yet. Something that was made. That's where we are. October 1st, 2025. A handful of images. A mystery with no answers. And a visitor from another star that looks wrong. The data is real. The mission happened. The object is out there, moving through our solar system as we speak, and we're standing here holding photographs of something we can't explain, looking at surfaces that shouldn't be smooth, looking at patterns that shouldn't repeat, looking at grooves that shouldn't be straight, and wondering, quietly, carefully, because this is the kind of question that changes everything, if this isn't natural, AC nice, then what is it? There's a moment in every investigation where you stop looking at the whole picture and start looking at the details, the cracks, the edges, the small things that don't line up, because that's where the truth hides. In the days following October 1st, that's exactly what happened with 3i Atlas. Scientists stopped staring at the full image, the mysterious visitor suspended in black, and started zooming in, frame by frame, pixel by pixel. And what they found? It wasn't just strange. It was impossible. Let's start with the basics. When you study an object in space, a comet, an asteroid, whatever, you're looking for patterns. Not the kind humans make, the kind nature makes. Randomness with rules. Craters scattered across a surface because of impacts over billions of years. Irregular shapes caused by gravitational forces and collisions. Cracks from thermal stress. Boulders where they fell. Chaos. But predictable chaos. That's what natural looks like. But 3i Atlas? It didn't look natural. It looked organized. The first thing researchers noticed were the grooves. In the initial images released by China, you could see them running across the surface. Long, narrow, parallel to each other. At first glance, you might think, okay, maybe that's from outgassing. Jets of gas escaping as ice sublimates, carving channels into the surface. Comets do that. It's not unheard of. But when a team at MIT ran edge detection software on the images, software designed to highlight boundaries and geometric features, the results were unsettling. The grooves weren't random, they were aligned. Perfectly aligned with the object's rotational axis. Meaning, as 3i Atlas spins, these grooves run along the spin direction like latitude lines on a globe. Symmetrical, evenly spaced. One researcher described it in a forum post as less like erosion and more like threading on a screw. And here's the thing. When you measure the spacing between the grooves, the distance from one to the next, it's consistent. Not approximately consistent. Exactly consistent. Within millimeters across hundreds of meters. That doesn't happen in nature. Erosion is messy. Sublimation is uneven. Thermal expansion creates cracks that branch and split and wander. But these grooves, they stayed straight. Parallel. Uniform. Like they'd been machined. Then there were the depressions. 3 of them. Maybe more, depending on how you count. Rectangular. Not kind of rectangular. Not if you squint and tilt your head. Geometrically rectangular. The largest one measured approximately 12 meters by 8 meters, based on shadow length analysis and the known distance of the imaging probe. Sharp corners. Clean edges. One team in Berlin ran the image through a shape recognition algorithm, the kind used in industrial quality control to detect defects in manufactured parts. The algorithm flagged it immediately. Match confidence, 94%. For context, when you run the same algorithm on natural rock formations, mesas, canyon walls, anything shaped by wind or water or time, you get match confidence below 30%. Because nature doesn't make rectangles, not at this scale, not with these proportions. But 3i Atlas did. And that depression? It wasn't alone. Scattered across the surface were smaller features. Rectangular pits, raised ridges forming right angles, sections where the texture changed abruptly like different materials had been joined together. In one image, a ridge ran for 40 meters, then stopped. Just ended. No tapering, no gradual fade, a hard stop, like a seam. By October 3rd, research teams across the world were doing the same thing. Overlaying grids, measuring angles, comparing dimensions. It's a technique called geometric analysis, and it's used to determine whether patterns are random or structured. You take a feature, and say one of those grooves, and you measure its angle relative to the object's axis of rotation. Then you measure the next groove and the next. If they're random, the angles will vary. A few degrees here, a few degrees there. Natural scatter, but if they're structured, the angles stay the same. And on 3i Atlas, they did. A team at Caltech published a preliminary analysis on October 4th. They measured 14 parallel grooves visible in the Chinese images. The angular deviation, the amount each groove varied from perfect alignment, averaged 0.3 degrees. 0.3 degrees. Over a span of 200 meters. To put that in perspective, if you tried to draw 14 parallel lines by hand, perfectly straight across the length of 2 football fields, you couldn't do it. Not without tools, not without precision instruments, not without intent. And then there was the thermal data. This is where things got really uncomfortable. Because temperature doesn't lie. When sunlight hits an object, it heats up. The side facing the sun gets warm. The side in shadow gets cold. Simple physics. And when a comet heats up, specific things happen. Ice sublimates, gas escapes. The surface cools through sublimation in some areas, warms in others depending on composition, angle, and rotation. You can model this, predict it, match observations to theory. But 3i Atlas didn't match. The thermal scans embedded in China's data, captured in infrared wavelengths, showed temperature variations that made no sense. Sections of the surface were warmer than they should be. Not by much. Just 4 or 5 degrees Kelvin above the predicted temperature based on solar heating models. But here's the problem. Those warm spots weren't on the sun-facing side. They were scattered, localized, clustered near the grooves, near the rectangular depressions, as if something underneath was generating heat. And then there were the cold zones, areas that stayed frozen, well below the sublimation temperature of water ice, even though they were in direct sunlight. Even at perihelion, the closest point to the sun, they should have been warming, venting, losing mass. But they weren't. It's like they were insulated, protected by something that doesn't sublimate, doesn't absorb heat the way ice or rock does, a material with properties we don't see in natural comets. One scientist put it bluntly in a private email that later leaked. This thermal profile looks more like a malfunctioning spacecraft radiator than a comet nucleus. Spectrometry added another layer to the puzzle. Spectrometry is how we figure out what things are made of. You analyze the light reflecting off an object, break it into wavelengths, and match those wavelengths to known materials. Ice reflects light one way, rock another, metal another. And 3i Atlas, it reflected light. Strangely, the spectrum didn't match water ice, didn't match carbon dioxide ice, didn't match silicate rock or iron or any common asteroid material. It was a mix, a composite. Some sections showed high reflectivity in certain wavelengths, like polished metal or glass. Other sections showed low reflectivity, like carbon-rich material or organic compounds. And the reflectivity wasn't uniform. It changed depending on which part of the surface you looked at. Like the object was made of different materials in different places, which again is weird. Comets are usually pretty uniform, ice mixed with rock and dust, homogeneous more or less. But 3i Atlas, it was heterogeneous, layered, structured. One researcher described it as less like a natural body and more like a composite hull. By the second week of October, something was happening in the scientific community. A shift. It started quietly, in private channels, in group chats, in emails between colleagues who'd known each other for decades. People were running the same analyses, reaching the same conclusions. And the conclusions were uncomfortable. A geologist in Tokyo ran fractal analysis on the surface features, a mathematical technique that measures complexity and randomness. Natural surfaces have high fractal dimensions, lots of small-scale variation. Irregularity at every zoom level. 3i Atlas scored low. Too smooth. Too regular. A planetary scientist in Paris compared the grooves to erosion patterns on Earth. Riverbeds, glacial valleys, wind-carved rock. No match. Not even close. An engineer in Munich, someone who designed spacecraft components, looked at the rectangular depression and the raised ridges around it. Their assessment? If I saw this on a blueprint, I'd call it a structural panel with reinforced edges. One by one, researchers were arriving at the same place. This didn't look like geology. It looked like engineering. And then someone found the markings. October 8th, a research assistant at the European Southern Observatory was processing one of the high-resolution images, adjusting contrast to bring out faint details. And there near one of the rectangular depressions, barely visible against the dark surface, shapes. Faint, shallow, maybe a few centimeters deep, based on shadow analysis. At first they thought it was noise. Image compression artifacts. But when they applied edge enhancement filters, the shapes became clearer. Symbols. Or at least, something that looked like symbols. Curved lines, angular forms, repeating elements. Not random scratches, not micrometeorite impacts, deliberate. The assistant posted the image in a Slack channel with a single question. Does anyone else see this? Within an hour, 3 other teams confirmed they'd seen similar markings in different images. Always near the depressions, always faint, always geometric. And the debate began immediately. Some said it was pareidolia, our brain seeing patterns that aren't there, like seeing faces in clouds. Others said it was surface erosion, natural weathering over millions of years. But a smaller group, a group that was growing, said something else. They said, this looks like writing. Let's be clear. No one was saying they could read it. No one was claiming to know what it meant. But the structure was there. Repeating elements, consistent spacing, directional flow. The kind of organization you see in language, in text, in communication. And if that's what it was, if those markings were intentional, placed there by something intelligent, then everything changed. Because you don't carve symbols into a rock. You carve them into something that matters, something you want to last, something you want to be found. By mid-October, the data was everywhere. Not in journals, not in official publications, but in preprints, in shared drives, in forum posts and Discord servers and Twitter threads. People were compiling the evidence. Geometric grooves aligned to rotational axis, rectangular depressions with sharp edges, thermal anomalies inconsistent with solar heating, reflectivity patterns suggesting composite materials, surface markings with structured organization, and the question kept coming up, over and over, in every thread, every analysis, every discussion. If this is a comet, why does it look like it was made on purpose? Because here's what we know about comets. They're ancient, formed in the outer regions of star systems, made of ice, rock, dust, shaped by gravity and time and random collisions. They don't have patterns, they don't have symmetry, they don't have straight lines or right angles or organized markings. They're chaotic, beautiful in their randomness. But 3i Atlas, it wasn't chaotic. It was precise, and precision implies purpose. On October 12th, a team at Johns Hopkins published a 12-page document titled Geometric Constraints on 3i Atlas Surface Features, Preliminary Analysis. The abstract was careful, clinical, almost cold, but the final line hit like a hammer. The observed features exhibit morphological characteristics inconsistent with known natural formation processes. Translation: we don't know what this is, but we know what it isn't. It isn't natural. And once you cross that line, once you admit that the patterns aren't random, that the structure isn't accidental, you have to ask the next question. The one nobody wants to ask. The one that changes everything. If it wasn't made by nature, then who made it? There's something you should know about scientists. They're not supposed to argue like this. Sure, they debate, they disagree, they publish papers that challenge each other's work. But it's usually polite, professional, evidence-based, calm. What happened in the 2 weeks after China released those images? That wasn't calm. That was something else entirely. It started on October 4th, 3 days after the images went public. 3 days of nonstop analysis, measurements, and whispered conversations in research labs across the world. And then the first official response came. Not from China, they were still silent, but from the International Astronomical Union, the organization that names celestial objects and coordinates global astronomy efforts. They released a statement, short, carefully worded. It acknowledged the images, confirmed they appeared to be authentic, and then said this: "We urge caution in interpreting surface features observed in recent imaging of 3i Atlas. Further analysis and independent verification are necessary before drawing conclusions about the object's composition or origin." Translation: everyone calm down. We don't know what this is yet. And for about 12 hours, that seemed to work. People took a breath, waited for more data, let the experts do their job. But then the preprints started dropping. If you're not familiar with how scientific publishing works, here's the short version. When researchers have findings, they write a paper. That paper goes through peer review. Other scientists check the work, make sure it's solid, then it gets published in a journal. That process takes months, sometimes years. But there's a shortcut. It's called a preprint. You write the paper, upload it to a public server, and boom, it's out there. No peer review, no gatekeepers, just raw research, available to anyone who wants to read it. It's fast, it's open. And in mid-October 2025, it became a battlefield. The first major preprint hit on October 6th. Title: Geometric Constraints on 3i Atlas. Surface Features, Evidence Against Natural Formation. Authors: a team of 6 researchers, 3 from Caltech, 2 from MIT, 1 from the University of Tokyo. The paper was 19 pages long, dense with measurements, diagrams, statistical analysis, but the abstract, the summary at the beginning, was clear. They'd measured the grooves, the depressions, the ridges. They'd run geometric analysis, compared the features to natural formations on Earth, on asteroids, on comets. And their conclusion? The observed surface characteristics exhibit a level of geometric precision inconsistent with stochastic processes. Alternative formation mechanisms should be considered. Alternative formation mechanisms? They didn't say artificial, but they didn't have to. Within 6 hours, the paper had been downloaded 80,000 times. Within a day, it was trending on Twitter, and the scientific community fractured. On one side, you had the skeptics. Not skeptics in a dismissive way, but in a scientific way. People who said, hold on, let's not jump to conclusions. A prominent astrophysicist at Cambridge published a response 2 days later. Title: Pareidolia and Pattern Recognition. Bias in the Analysis of 3-Eye Atlas Imagery. Their argument was simple. Humans see patterns. It's what we do. We see faces in clouds, shapes in random noise, order in chaos, and when you're analyzing low-resolution images of a distant object, compressed and transmitted across millions of miles, artifacts happen. Pixels align in ways that look geometric but aren't. Shadows create edges that seem sharp but are just tricks of light and angle. The grooves could be thermal fractures from repeated heating and cooling cycles. The rectangular depressions could be impact craters viewed at specific angles that make them look more regular than they are. The thermal anomalies could be subsurface ice pockets with different conductivity or compositional variations we don't fully understand yet. And the markings? Pareidolia. Pattern recognition gone wild. The paper ended with this line: extraordinary claims require extraordinary evidence. The current data, while intriguing, does not meet that threshold. It was a fair point. Reasonable point. And for a lot of scientists, maybe even most, it was the right point. Because the alternative, the idea that 3-Eye Atlas might not be natural, that was too big, too disruptive, too uncomfortable, easier to wait. Demand more data, stay cautious. But on the other side, you had the ones who couldn't look away, the ones who kept zooming in on those images, kept running the numbers, kept finding things that didn't add up. On October 10th, another preprint dropped. Title: Non-Random Thermal Distribution. Observed in Chinese probe data. Implications for internal structure. This one focused on the heat signatures. The authors, a mix of planetary scientists and thermal engineers, ran simulations. They modeled how 3-Eye Atlas should heat up based on its distance from the sun, its rotation rate, its estimated composition. And then they compared those models to the actual thermal data from China's probe. The match? Terrible. The models predicted heating patterns that didn't appear. And the real data showed heating patterns that shouldn't exist. Localized warm spots with no corresponding surface activity. Cold zones that defied solar flux predictions. The paper's conclusion was cautious but firm. The thermal profile suggests the presence of subsurface structures with non-uniform thermal conductivity, inconsistent with a homogeneous icy or rocky body. Subsurface structures, like compartments, layers, insulation, the kind of thing you'd find in a designed object, not a comet. By mid-October, the divide was obvious. You had the mainstreamers, let's call them the cautious, saying, we need more data, don't speculate. And you had the challengers, let's call them the bold, saying, the data is already here, stop ignoring it. And neither side was backing down. Press conferences were held. On October 12th, NASA's Planetary Defense Coordination Office gave a briefing. Calm, measured. They acknowledged the images, said they were interesting and worth further study, and emphasized that natural explanations remain the most parsimonious. Parsimonious, a fancy word for simplest. Occam's razor, the idea that the simplest explanation is usually the right one, and in science, natural is always simpler than artificial. But then a reporter asked, if these features are natural, why can't you explain them? Long pause. We're working on it. That clip went viral. Meanwhile, in private channels, Slack groups, Discord servers, email chains, the real conversations were happening, and they were brutal. Scientists accusing each other of bad faith, of ignoring evidence, of seeing what they wanted to see. One message leaked later to a journalist: if you publish that paper, you're done. No one will take you seriously again. Another: we've been looking at this for 2 weeks and you're telling me you see nothing unusual? What are you afraid of? Friendships fractured, collaborations ended. People who'd worked together for decades stopped speaking. Because this wasn't just about data anymore. It was about belief, about what you were willing to consider possible. And then social media got involved. Oh, it got very involved. Someone at, probably a grad student with too much time and too much Photoshop skill and that started making comparison images, side by side. On the left, 3-Eye Atlas. Those grooves, those depressions, that smooth, organized surface. On the right, a natural comet, cratered, jagged, chaotic. Caption: one of these is from another star, one of these is from our solar system. Guess which is which? 50,000 retweets in a day. Then someone made another comparison. Left, 3-Eye Atlas surface detail. Right, the hull plating of the International Space Station. Caption: can you tell the difference? And the comments? Half the people said, this is ridiculous, you're seeing what you want to see. The other half said, holy shit. There were other comparisons too. 3-eye atlas next to eroded monuments on Earth, ancient stone structures with clean lines and geometric shapes, next to microchips, circuit boards, manufactured components, next to other interstellar objects. Oumuamua, with its cigar-like shape and strange acceleration, Borisov, which looked like a normal comet but came from beyond, and every comparison raised the same question. Where does 3-eye atlas fit? It didn't look like the natural objects, but it also didn't look exactly like the artificial ones. It was somewhere in between, or maybe somewhere beyond. On October 14th, a documentary filmmaker posted a 10-minute video essay. Title: 3-eye atlas, the object that doesn't belong. It went viral, 2 million views in 48 hours. The video laid out the evidence clearly, calmly, showed the images, explained the geometry, walked through the thermal data, and at the end it asked, if this is natural, show me another object like it, anywhere, in our solar system, in all the comets and asteroids we've ever studied. Show me one that looks like this. Silence. Fade to black. You can't, because there isn't one. The comment section was chaos, some people calling it fear-mongering, irresponsible, dangerous, others saying it was the most important question humanity had ever faced, and in the middle, thousands of people just wondering, trying to make sense of something that didn't make sense. But here's the thing that most people didn't see. The public debate, the Twitter threads, the YouTube videos, the news articles, well, that was all surface level. Behind the scenes, in the places where decisions actually get made, a different conversation was happening. Late October, a closed-door meeting at NASA headquarters in Washington. No press, no minutes released, just a handful of senior officials, a few scientists, and representatives from the Department of Defense. The topic? 3-eye atlas. Specifically, what do we do if it's not natural? Not is it natural? What do we do if it's not? Because here's the reality. Space. Agencies plan for everything. Asteroid impacts, solar storms, equipment failures. But this, an interstellar object that might be artificial, there was no protocol for that. No plan, no framework, no idea how to even begin addressing it. One person in that meeting, a senior scientist whose name hasn't been released, reportedly said, if China's probe saw what we think it saw, we need to decide how to tell people, or if we tell people at all. Someone else responded, the images are already public. We're past that point. No, the images are public, but the interpretation? That's still ours to control. For now. Silence, then. And what happens when we can't control it anymore? No one had an answer, because that's where we were by late October. The images were real, the data was real, the patterns were real. But the meaning, that was still up for debate, and the debate was tearing the scientific community apart. On one side, people who believed in natural explanations because that's what science teaches us. That's what the evidence has always supported. That's what makes sense. On the other side, people who looked at those grooves, those depressions, those thermal readings, and couldn't make them fit into any natural model. And in the middle, most people, just trying to figure out what to believe. A professor at Harvard, someone respected, cautious, not prone to wild speculation, gave an interview on October 16th. The interviewer asked, do you think 3-eye atlas could be artificial? Long pause. I think we're asking the wrong question. What's the right question? The right question is, why are we so afraid to consider it? Another pause. We have data that doesn't fit natural models. We have features that look engineered. We have patterns that repeat with precision we don't see in nature. And instead of investigating that seriously, we're dismissing it. We're inventing explanations that don't quite work because they're more comfortable than the alternative. And what's the alternative? That we're not alone. That we've never been alone. That the galaxy is full of things, objects, remnants, messages, and we're only just now learning to see them. Do you believe that? I believe we should stop being afraid to ask. That interview was watched 5 million times, and it changed nothing. Because belief isn't about evidence, it's about what you're willing to accept as possible. By the end of October, the divide was complete. The cautious published papers calling for restraint, more observation, better data. The bold published papers arguing the current data was already extraordinary. Forums were locked. Comments were disabled. Researchers stopped engaging publicly because every statement was dissected, attacked, weaponized. And 3-eye atlas, it kept moving. Outward, silent, unconcerned, past Mars, toward the asteroid belt, heading back to interstellar space, fading. Soon it would be too far to study, too faint to image, and we'd be left with what we had. A handful of photographs, a mountain of analysis, and two opposing interpretations that couldn't both be right. But here's the thing no one was saying out loud. Not in the papers, not in the press conferences, not in the public debates. The thing that was whispered in private meetings, in late-night messages, in conversations behind closed doors. What if both sides are wrong? What if 3i Atlas isn't fully natural, but also isn't fully artificial? What if it's something we don't have a category for yet? Something that blurs the line between geology and engineering, between object and machine. What if we're arguing about the wrong framework entirely? And beneath that question, an even darker one. One that space agencies were starting to ask themselves. One that kept people awake at night. What if China's probe saw something we've been trying not to see? What if there are more of these objects? What if they've been passing through our solar system for years, decades, and we've been calling them comets, asteroids, natural debris, because it was easier than admitting what they might actually be? October 16th, 2025, 9:47 a.m. Eastern Time. A document appears on Archive, the public server where scientists share research before peer review. 47 pages long. Title: Structural Anomalies in 3i Atlas, Evidence for Non-Geological Origin. For the first few hours, only a handful of people notice, researchers who monitor the site daily, grad students killing time between classes, a few journalists who track space-related submissions. But by noon it's everywhere. Because this isn't just another opinion piece, another hot take, another speculative essay from someone with a blog and a telescope. This is different. This is rigorous, detailed, methodical. This is the paper people have been waiting for. The one that doesn't just ask questions, the one that answers them. Let's talk about who wrote it, because that matters. When someone makes a bold claim, the first thing people ask is, who are you and why should I listen? This paper had 14 co-authors, not random people, not fringe theorists, established researchers, people with decades of experience, PhDs from MIT, Caltech, Cambridge, Tokyo, engineers who'd worked on actual spacecraft, astronomers who discovered asteroids, tracked comets, published hundreds of papers in respected journals. These weren't people chasing clicks or controversy. These were people who'd built their careers on being careful, conservative, evidence-based, and they were putting their reputations on the line. Because once you publish something like this, once you suggest that an interstellar object might not be natural and there's no taking it back. You're marked. People remember, and if you're wrong, your career is over. So the fact that 14 respected scientists were willing to sign their names to this document, that meant something. The paper opens with a simple statement. This analysis evaluates the physical characteristics of 3i Atlas as observed in imaging and spectrometric data released by the China National Space Administration. Our objective is to determine whether these characteristics are consistent with natural formation processes or require alternative explanations. Clinical, neutral, professional, no sensationalism, no wild claims. Just let's look at the data and see where it leads. And then for the next 40 pages, they do exactly that. The paper is divided into 6 sections. Each one focuses on a specific feature of 3i Atlas, and each one systematically shows why that feature doesn't fit natural models. Let's walk through them. Section 1, Surface Grooves and Channel Morphology. The grooves on 3i Atlas, those parallel lines running across the surface, had been debated since the images first dropped. Some said they were thermal fractures, others said sublimation channels. This paper measured them. Precisely. Width, 1.2 to 1.8 meters, with minimal variation. Depth, 0.4 to 0.6 meters, based on shadow analysis. Spacing, 8 to 12 meters apart, consistent across 200 plus meters of visible surface. Alignment within 0.3 degrees of parallel over that entire span. Then they compared those measurements to natural channels. Riverbeds on Earth, lava tubes on Mars, sublimation channels on comets like 67P, which the Rosetta mission studied up close. The comparison? Not even close. Natural channels are irregular. They branch. They widen and narrow. They curve and meander because the processes that create them, water flow, gas venting, thermal stress, are chaotic. But these grooves, uniform width, constant depth, perfect spacing. The paper's conclusion, the aspect ratios and geometric consistency of these features are more consistent with machined or molded channels than with erosional or sublimation-driven processes. Machined or molded. Engineering terms, not geology terms. Section 2, Thermal Emission Patterns. This section focused on the heat signatures. Remember those warm spots? The ones that didn't align with solar heating? The paper analyzed them in detail. They mapped the thermal distribution across the entire visible surface, compared it to models of how a natural object should heat up based on its rotation, distance from the sun, and estimated composition. And the models didn't match. Not even close. Natural objects heat unevenly, yes, but the pattern is predictable. The sun-facing side gets hot, the shadowed side stays cold. Rotation creates gradients. But 3i Atlas showed localized heat sources, hotspots deep beneath the surface, radiating outward. No corresponding surface vents, no visible outgassing, no jets or plumes. Just heat. Coming from inside. The paper ran simulations, tested different scenarios. Radioactive decay, too weak, would have dissipated billions of years ago. Chemical reactions, possible, but would require specific compounds in specific concentrations that don't match the spectroscopic. Data. Subsurface ice sublimating and venting through hidden channels? Maybe. But that should create pressure. Should cause outbursts. Should show up in brightness variations. None of that was happening. The conclusion? The observed thermal profile suggests internal heat sources inconsistent with passive thermal models for inert bodies. The distribution pattern resembles active thermal management systems rather than natural geothermal processes. Active thermal management, like a radiator, like a cooling system, like something designed to regulate temperature. Section 3, reflectivity and material composition. This one was technical, but the core idea was simple. When you shine light on something, the way it reflects tells you what it's made of. Ice reflects one way, rock another, metal another, and 3i Atlas? It reflected light like it was made of multiple different materials, not mixed together randomly like you'd expect from a natural aggregate of ice and dust, but in distinct zones, layered, organized. Some sections had high reflectivity in visible wavelengths, suggesting smooth, polished surfaces or crystalline structures. Other sections had low reflectivity, carbon-rich, matte, absorbing light rather than reflecting it, and the boundaries between these zones? Sharp. Not gradual transitions, not blended regions, defined edges, like panels, like different components joined together. The paper compared this to natural objects. Comets are messy. Dust mixed with ice. Organics scattered throughout. Reflectivity varies, sure, but it's gradual, chaotic. Then they compared it to manufactured objects. Spacecraft, satellites, probes. Those have distinct sections, solar panels, thermal blankets, hull plating, antennas, each made of different materials for different purposes. And the reflectivity pattern? It matched that model better. The paper didn't say it was a spacecraft, but it said the reflectivity pattern was more consistent with composite manufactured materials than homogeneous natural aggregates. Section 4, rotational stability and mass distribution. This section was about how 3i Atlas spins. When you have a natural object, an asteroid, a comet, whatever, its rotation is usually messy, tumbling, wobbling, changing over time as it vents gas or sheds material. But 3i Atlas, its rotation was stable, extremely stable. It spins on a single axis, period of roughly 8.3 hours. No wobble, no precession. For a natural object, that's unusual. It means the mass is distributed evenly, symmetrically, like the object has a uniform density throughout, or like the mass is deliberately balanced. Natural objects aren't balanced. They're lumpy, irregular, dense in some places, porous in others. But if you were designing something, if you wanted it to spin smoothly, to remain stable, to not tumble chaotically through space, you'd balance the mass distribution. You'd place heavier components near the center, lighter ones at the edges. You'd engineer it. The paper ran simulations, showed that for 3i Atlas to have this kind of rotational stability naturally, it would need a very specific internal structure. Possible, yes. Likely, no. Conclusion. The observed rotational characteristics suggest internal mass distribution consistent with designed equilibrium rather than stochastic accretion. Designed equilibrium, another engineering term. Section 5, geometric alignments. This was the most damning section, because geometry doesn't lie. The paper cataloged every major surface feature visible in China's images, the grooves, the depressions, the ridges, the texture changes, and then they measured the angles, how each feature aligned relative to the object's rotational axis, relative to each other, relative to the overall shape, and they found something remarkable. The features aligned within 0.3 degrees, across multiple surface zones, across hundreds of meters. Let me put that in perspective. If you tried to build a structure on Earth, a building, a bridge, whatever, and you wanted the components to align within 0.3 degrees, you'd need precision tools, laser levels, computer-guided machinery. You couldn't do it by hand. And nature? Nature doesn't build to tolerances like that. The paper compared 3i Atlas to other small bodies, asteroids like Bennu and Ryugu, which we've studied up close with spacecraft. Comets like 67P, which Rosetta orbited for years. Those objects have features? Sure. Boulders, cracks, depressions, but nothing aligns, nothing repeats with precision, because they're shaped by chaos, by impacts and sublimation and billions of years of random forces. But 3i Atlas, precise, aligned, organized. The conclusion was careful. The geometric consistency across spatially separated features is inconsistent with random formation mechanisms and suggests coordinated structural design. Coordinated structural design, not natural, designed. Section 6, Synthesis and Comparative Analysis. The final section pulled it all together, took those 6 features and asked, what kind of object has all of these characteristics? They built comparison tables. On one side, natural objects, comets, asteroids, interstellar bodies like Oumuamua and Borisov. On the other, manufactured objects, spacecraft, probes, satellites, and then they scored 3i Atlas against both categories. Surface features, more consistent with manufactured. Thermal profile, more consistent with manufactured. Reflectivity, more consistent with manufactured. Rotational stability, more consistent with manufactured. Geometric precision, more consistent with manufactured, 5 out of 6. The paper didn't say 3i Atlas is artificial, but it said this. The observed characteristics are more consistent with design structures than with stochastic accretion or impact-driven morphology. And then in the final paragraph, while natural explanations cannot be entirely excluded, none of the proposed mechanisms adequately account for the full suite of observed features. Alternative hypotheses, including non-geological origin, warrant serious consideration. Non-geological origin, a careful phrase, a clinical phrase, but everyone reading it knew what it meant. This might not be natural, this might be something else. The reaction was immediate. Within hours, the paper had been downloaded 200,000 times. Within a day, it was trending on every platform, Twitter, Reddit, YouTube, mainstream news outlets, and the phrase that kept appearing in headlines, in articles, in discussions was this: interstellar artifact. Not as a joke, not as conspiracy theory, as a scientific hypothesis, an actual legitimate possibility being discussed by actual legitimate scientists. Because here's the thing, you can ignore one anomaly, dismiss it as a fluke, a measurement error, a misinterpretation. You can ignore 2, maybe 3, but 6 separate features all pointing in the same direction? That's not a fluke, that's a pattern. And the most unsettling part? No one could prove it wrong. People tried. Skeptics published responses, alternative explanations, natural mechanisms that might explain one feature or another, but nothing explained all of them. Nothing fit the whole picture. One critic suggested the grooves were thermal fractures caused by repeated expansion and contraction over millions of years. Okay, but that doesn't explain the geometric precision, the alignment within 0.3 degrees. Another suggested the thermal anomalies were subsurface ice pockets with unusual thermal conductivity. Fine. But that doesn't explain why the heat sources are localized, stable, and don't correspond to any surface activity. Someone else proposed that the reflectivity patterns were caused by different layers of ice and organics exposed by sublimation. Maybe. But that doesn't explain the sharp boundaries, the distinct zones, the composite nature of the materials. Every natural explanation worked. Partially. But none worked completely. And when you have 6 anomalies and you need 6 different explanations, each one requiring special conditions, at some point you have to ask, am I trying to explain the data or am I trying to avoid the conclusion? On October 18th, a mainstream science journal, Nature, published an editorial, not an endorsement of the machine hypothesis, but an acknowledgement that the conversation had changed. The title, 3i Atlas and the Limits of Natural Explanation. The opening line, when data challenges our assumptions, we have 2 choices, expand our models or expand our imagination. With 3i Atlas, we may need to do both. It was a signal from one of the most respected voices in science, saying this is real, this deserves attention, this is not fringe. And behind the scenes, behind the press releases and the public debates, space agencies were panicking, not publicly, but quietly. Because if 3i Atlas was artificial, if it was a probe, a relic, a machine sent by someone, something, from another star, then everything changed. Every assumption about our place in the universe, every plan, every protocol, every model of how we interact with space, gone, rewritten, because we weren't alone. And we'd never been alone. We'd just been too blind or too scared to see. On October 20th, a hashtag started trending. Dane. What is Watlas? Millions of tweets, arguments, theories, fear, excitement, people posting the images, the data, the paper, asking the same question over and over: what is this thing? And the answer, the only honest answer, was, we don't know, but we know what it's not. It's not a comet. It's not an asteroid. It's not like anything we've ever seen before. And maybe, just maybe, it's something we were never supposed to find. As October drew to a close, 3i Atlas was already 300 million kilometers from Earth, fading, silent, still moving, still defying explanation, and humanity was left holding a 47-page document that systematically dismantled every natural explanation and offered only one alternative: that somewhere, out there, in the vast cold dark between the stars, someone built this, someone sent it, and it passed through our solar system, ancient and silent, carrying secrets we might never understand, unless we're willing to ask the question we've been avoiding, the question that changes everything. Are we alone, or are we just now learning to see the truth? There's a moment in every story where the questions change, where you stop asking what happened and start asking what it means. For weeks, the conversation around 3i Atlas had been technical: data, measurements, analysis, scientists arguing about grooves and thermal patterns and geometric alignments. But by late October, something shifted. The conversation left the laboratories, left the research papers and the peer reviews, and entered a much older, much deeper space. The space where humanity asks the questions that matter most. Who are we? Where do we come from? Are we alone? Philosophy, theology, existential weight. Because if 3i Atlas isn't natural, then everything changes. It started quietly. October 21st, a philosophy professor at Oxford published an essay, not in a science journal, in a philosophy journal. Title: The Epistemic Crisis of Contact, What We Owe to Evidence We Cannot Ignore. The essay wasn't about whether 3i Atlas was artificial. It was about what happens to us, to human thought, to human belief, when we're confronted with evidence that challenges our deepest assumptions. The professor wrote, "For centuries we have operated under the assumption that we are alone, not because the evidence supports it, but because the absence of evidence allowed it. 3i Atlas changes the calculus. It forces us to confront a possibility we have kept at arm's length, that the universe is not empty, that intelligence is not rare, that we have been sharing the galaxy with others, and we simply didn't know how to look." The essay went viral. Not among scientists, among everyone. Because this wasn't about data anymore. This was about meaning. Within days, theologians were weighing in. A Catholic priest in Rome, a rabbi in Jerusalem, an imam in Cairo, a Buddhist monk in Kyoto, each from different traditions, different beliefs, but all asking the same question: if we are not alone, what does that mean for us? For some religious traditions, the idea of life beyond Earth wasn't troubling. It was expected. The universe is vast. God, or the divine, or the cosmos, is infinite. Why wouldn't there be others? But for others, the implications were harder. Because if someone else built 3i Atlas, if there's intelligence out there, ancient and capable of crossing the stars, where do we fit? Are we special, chosen, unique? Or are we just one more species in a galaxy full of life? One theologian put it this way: the question is not whether God created others. The question is whether our story is the only story that matters. And that question cuts deep. Astrobiologists entered the conversation too. These are the scientists who study life, how it forms, where it exists, what it needs to survive. For decades they'd been searching, looking for biosignatures on exoplanets, analyzing meteorites for organic compounds, sending probes to Mars and Europa and Enceladus, searching for microbial life. But 3i Atlas wasn't microbial. It wasn't primitive. It wasn't simple. If it was artificial, it represented something far more advanced than bacteria in ice. It represented technology. And that changed the question from, is there life out there, to what has life out there achieved? A researcher at SETI, the Search for Extraterrestrial Intelligence, said this in an interview. "We've been listening for radio signals, searching for deliberate messages. But what if the message isn't a signal? What if the message is the object itself? What if 3i Atlas is the hello? A probe, a calling card, a way of saying, we exist, we were here, we are watching." But that opens up a cascade of questions. Questions that don't have easy answers. Questions that keep you awake at night. Let's walk through them. If 3i Atlas is a probe, if it's something designed to travel between stars, to observe, to collect data, who sent it, where did it come from, and why? Are they watching us right now, waiting to see if we notice? Have they been watching for decades, centuries, millennia, as we slowly crawled our way into space and learned to look up? Or is this probe ancient beyond measure, launched by a civilization that's long gone, still carrying out its mission millions of years after its creators turned to dust? And if they are watching, what do they think of us? What do they see when they look at Earth? A species on the edge of greatness or the edge of collapse? Do they see potential or danger? And most unsettling of all, are we the first civilization they visited? Or just the latest? If 3I Atlas is debris, if it's a fragment, a piece of something larger that broke apart long ago, then what kind of civilization produces wreckage that crosses light years? How advanced do you have to be to build objects so durable they survive the void of interstellar space for millions of years? And if this is just debris, a leftover, a discard, a forgotten piece of something that once mattered, how much more is out there? How many other fragments are drifting through the galaxy, invisible, unnoticed, until they happen to pass close enough for us to see? And what does it say about the scale of intelligence in the universe if this geometrically precise, thermally active, structurally sound object is just trash? If 3I Atlas is a message, if it's meant to communicate something, then why is it silent? No radio signals, no transmissions, no attempt to make contact, just movement, presence. A surface covered in patterns we don't understand and can't decode. Maybe the message isn't meant for us. Maybe it's meant for someone else and we're just intercepting it by accident. Or maybe the message is the object itself, its existence, its structure, its impossible precision. Maybe the message is, we are here. We have always been here. Look harder. And if that's the message, what are we supposed to do with it? These questions don't have answers. They just spiral outward, each one leading to 10 more. And by late October, people all over the world were asking them. Not just scientists, not just philosophers, everyone. Teachers in classrooms, parents at dinner tables, friends in coffee shops, strangers on the internet, arguing and wondering and trying to make sense of something that doesn't fit into any framework we've ever built. Because this isn't abstract anymore. This is real. There are photographs, data, a 47-page analysis by serious scientists, and the implication, the unavoidable, undeniable implication, is that we might not be alone, that we might never have been alone. On October 23rd, someone posted a question on Reddit. Simple, direct. If 3I Atlas is artificial, does that mean Oumuamua was too? And that's when things got even stranger. Let's rewind to 2017. October, a telescope in Hawaii spots something unusual, an object moving fast. Too fast to be bound to the sun. Interstellar origin. The first one ever confirmed. They name it Oumuamua, Hawaiian for scout or messenger. At first, everyone's excited, an interstellar visitor, a piece of another star system drifting through ours. But then the observations start coming in, and they're weird. Oumuamua is elongated, really elongated, shaped like a cigar or maybe a pancake, depending on how you interpret the light curve. Ratio of 10:1, length to width. No natural object we've ever seen looks like that. And then, as it's leaving the solar system, it accelerates. Not a lot, but measurably. A small push, away from the sun, that gravity alone can't explain. Scientists scramble for explanations. Outgassing. Jets of gas escaping as ice sublimates, pushing the object like a rocket. But here's the problem. No one sees a coma, no tail, no jets. It's accelerating. But there's no visible mechanism. Some scientists say the outgassing is just too faint to detect. Others say the object is tumbling in a way that makes the jets hard to spot, and most people accept that. Move on. File it under unusual but explainable. But a few people, a very few, say something else. They say, what if it's not outgassing? What if it's something else? One of those people is Avi Loeb, a Harvard astronomer, respected, serious. He publishes a paper suggesting Oumuamua might be a light sail, a thin reflective structure, artificial, pushed by radiation pressure from the sun. The backlash is immediate. People call him reckless, attention-seeking, damaging to science. Because suggesting an interstellar object might be artificial? That's not something you do lightly, but Loeb doesn't back down. He says, the data doesn't fit natural models, so why are we clinging to them? And most of the scientific community ignores him. Until now. Because now in October 2025, people are looking at Oumuamua again, with new eyes, with the context of 3I Atlas, and they're asking, what if Loeb was right? What if Oumuamua wasn't natural either? The elongated shape, the non-gravitational acceleration, the lack of visible outgassing, all of it could be explained if it was a thin, lightweight sail. And if Oumuamua was a sail, and if 3I Atlas is artificial, then how many others have there been? How many interstellar objects have passed through our solar system? And we called them comets, asteroids, natural debris, because it was easier than admitting what they might actually be. A researcher at Johns Hopkins runs a quick calculation. Based on the number of interstellar objects we've detected so far, just 3, Oumuamua, Borisov, and 3I Atlas, they estimate how many must pass through undetected. The answer? Hundreds, maybe thousands, every year. We only spot the ones that come close enough and bright enough. The rest drift by, invisible, which means if even a small percentage of those are artificial, if even 1 in 100, then the galaxy is full of these things. Probes, sails, fragments, messages, a vast network of objects drifting through the dark, launched by civilizations we've never met and might never understand. And we're just now starting to notice. That realization settles over the scientific community like a weight, because it means we've been blind, not through incompetence, not through ignorance, but because we didn't know what to look for. We assumed everything moving through space was natural, asteroids, comets, debris from the formation of solar systems. We built our models around that assumption, and those models worked. For decades, for centuries, until they didn't. Until objects started showing up that didn't fit, and instead of questioning the models, we questioned the data. We invented new explanations, stretched the definitions, added epicycles, because admitting the alternative, that some of these objects might not be natural, was too big, too scary, too world-changing. But now the data has piled up too high to ignore, and the question has shifted. We're not asking if we're alone anymore. We're asking, have we been visited before and didn't notice? A documentary filmmaker interviews a physicist. The question is simple. If these objects are artificial, why haven't we heard from whoever made them? The physicist pauses, thinks, then says, maybe we have. Maybe we just didn't recognize it as communication. What do you mean? We're looking for signals, radio waves, messages in a language we can decode. But what if the communication is the object itself? What if the message is, we exist, we travel, we endure? What if they don't need to say anything more than that? But why send something if you're not going to communicate? Maybe they did communicate? Millions of years ago, and now these objects are just echoes. Relics of a conversation that ended long before we existed. Silence. That's a lonely thought. Yes, but it's also a hopeful one. Because if they sent these objects even as echoes, it means they wanted to be remembered. They wanted to leave a mark. And we found it. We saw it. We're listening now, even if the conversation is over. By the end of October, the conversation around 3I Atlas is completely transformed. It's no longer about grooves and thermal readings. It's about what it means to be human in a universe we don't fully understand. It's about humility, wonder, fear, the realization that we are small, that our planet is small, that our sun is one of billions and our galaxy is one of trillions. And somewhere out there in all that vastness, someone else looked up, someone else wondered, someone else built something and sent it into the dark, hoping it would endure. And it did. It crossed light years, survived the void, arrived here, and we saw it. Not clearly, not perfectly, but we saw it. And that changes everything. A priest in a small church in Montana gives a sermon. He talks about 3I Atlas. He says, "For years people have asked me, 'Father, do you think there's life out there?' And I've always said, 'I don't know. But I know God is infinite, and infinity has room for more than just us.' Now we have this object, this thing. And we don't know what it is, but we know it's not ours. It came from somewhere else, from someone else. And people are scared. They're asking, what does this mean for us? For our faith? For our place in creation?" And I say it means we are not the center. We never were. But that doesn't make us less important. It makes us part of something bigger, something we're only beginning to see. The universe is vast, and maybe, just maybe, we are not alone in trying to understand it. The church is silent, but outside in the parking lot, people stand together, looking up at the stars, wondering. That's where we are. Late October 2025. An object from another star drifting through our solar system, covered in patterns we can't fully explain, and humanity standing beneath it, asking questions we've never had to ask before. Not just are we alone, but have we ever been alone? Has the galaxy been full of travelers, explorers, messengers, machines, and we just didn't notice? What else have we missed? What else is out there, right now, passing by, waiting for us to look up and see? The data from China doesn't answer these questions. It just makes them unavoidable. And as 3i Atlas continues its silent journey outward, past Mars, past the asteroids, toward the edge of our solar system and beyond, we're left standing here, changed. Not because we found proof of alien life, but because we found proof that the universe is stranger, richer, and more full of mystery than we ever imagined. And once you see that, you can't unsee it. The sky is no longer empty. It's full of possibility, full of questions, full of objects we might finally be learning to recognize. And that changes who we are. November 1st, 2025. 3i Atlas is 380 million kilometers from Earth, and fading. Not dramatically, not suddenly, just gradually dimming as it moves farther and farther away. Beyond Mars now, past the orbit where the red planet hangs in its slow dance around the sun, heading toward the asteroid belt. And beyond that, the outer solar system. Jupiter, Saturn, the frozen edge where sunlight barely reaches, and then back into interstellar space, the dark between stars, where it came from, where it's going, and it will not return. Observatories around the world are still tracking it. Telescopes pointed at a single point of light. That's all it is now. At this distance with this brightness, a dot, no detail, no grooves, no rectangular depressions, just a faint speck requiring long exposures and sensitive instruments just to confirm it's still there. The images from China, those sharp, haunting close-ups, remain the only detailed evidence we have. Frozen in time. October 1st, the moment we got close enough to see, and we'll never get that close again, because China has released no further data, no follow-up images, no additional scans, no clarification on how they did it, when they launched the probe, or why they chose to share what they shared. Just silence, and no other nation admits to having sent anything. NASA says they didn't. ESA says they didn't. JAXA, Roscosmos, every space agency on record, says no. Which means those images, that brief, impossible glimpse of something we don't understand, are all we have. And they explain nothing. Let's be honest about where we are. A month has passed since those images appeared, a month of analysis, debate, papers, arguments, and we're no closer to an answer than we were on October 1st. We have more data now, yes. More measurements, more theories. But no consensus, no clarity, no definitive explanation that satisfies everyone. The scientific community is still fractured, still divided between those who say natural, just unusual, and those who say we need to consider alternatives. Papers are being submitted, peer review is happening, conferences are being scheduled for early 2026. There will be panels, presentations, debates that last for hours, and maybe eventually something resembling consensus will emerge. But the object itself, it doesn't care. It doesn't wait for us to figure it out. It just moves. There's something almost cruel about that. We saw something extraordinary, something that challenges everything we thought we knew about interstellar objects. We asked questions, big questions, the kind that shake foundations. And the object's response? Nothing. It doesn't slow down to let us get a better look. It doesn't signal, doesn't transmit, doesn't offer any hint of intent or origin. It simply continues on its trajectory. The same trajectory it's been on for how long? Millions of years? Billions? We don't know. We don't know where it came from, what star system birthed it or built it. We don't know how long it's been traveling, and we don't know where it's going. Just away. Away from the sun. Away from Earth. Away from any chance we have of understanding it. On November 3rd, a graduate student at Caltech runs the numbers, calculates how long 3i Atlas will remain visible, how long before it fades below the detection threshold of even our best telescopes. The answer, 6 months. Maybe 8 if we're lucky and conditions are perfect. By mid-2026, it'll be too faint, too far, and then it'll be gone. Not destroyed, not stopped, just invisible. Out there, somewhere, still moving through the dark, but beyond our reach, forever. That realization settles over the research community like snow, quiet, cold, final. Because it means this is it. This is all the data we're going to get. The images from China, the measurements from ground-based telescopes, the spectroscopic data from those few weeks when the object was close enough and bright enough to study. That's the entire archive of human knowledge about 3i Atlas, and it has to be enough. Even though it's not. Even though it leaves more questions than answers. It has to be enough. Because the object is leaving. And we can't follow. Some people suggested it. In the days after the Chinese images went public, there were proposals. Emergency missions, fast-track spacecraft, probes designed to intercept 3i Atlas before it left the inner solar system. The technology exists. Barely. But it exists. Ion drives, solar sails, gravity assists past Jupiter. You could, in theory, build something fast enough to catch up, not quickly, not cheaply, but possible. And for a few days, space agencies actually considered it. Meetings were held, budgets were discussed, proposals drafted. But then reality set in. The cost, tens of billions of dollars. The timeline, years to design, build, and launch. The risk, astronomical. You're chasing a target moving at 40 kilometers per second. One mistake, one miscalculation, and you miss. And the political will, non-existent. Because despite all the excitement, all the debate, all the headlines, most people don't care enough, or they care, but not enough to justify that kind of spending. Not when there are problems here, on Earth. That needs solving. So the proposals were shelved, tabled for future consideration, and 3i Atlas continued moving. Unconcerned, there's a melancholy to watching it go. Astronomers who've spent the last month staring at this object, analyzing every pixel of those images, measuring every feature, now watching it fade. One astronomer described it in an interview. It's like meeting someone extraordinary, someone who changes how you see the world, and then watching them walk away, knowing you'll never see them again. You want to call out, ask them to stay, to explain, but they just keep walking, and all you can do is remember. That's what this feels like. A brief encounter with something profound. And then, absence. But here's the thing. Even as 3i Atlas fades, even as it becomes just a point of light and then nothing at all, it's already changed us. Not through answers, through questions. Because we can't unsee what we saw. We can't unthink the thoughts that those images provoked. The scientific community will argue for years about whether 3i Atlas was natural or artificial. Papers will be published on both sides. Evidence will be reanalyzed. New models will be proposed. And maybe someday consensus will emerge, or maybe it won't. Maybe 3i Atlas will remain forever ambiguous. A Rorschach test, a mirror that reflects back whatever we bring to it. Those who believe we're alone will see natural processes. Unusual, yes, but explainable. Those who believe we're not will see engineering. Design, intent, and both sides will have evidence. Both sides will have logic. Both sides will be able to defend their position. Because the truth is, we don't know. And maybe we'll never know. There's something humbling about that. In an age where we can measure the universe to stunning precision, where we can detect gravitational waves from black holes colliding billions of light years away, where we can image the event horizon of a supermassive black hole, where we can sequence the human genome and edit it with molecular scissors. We can't definitively say what 3i Atlas is. A visitor from another star passes through our solar system. We get close-up images, and we still don't know. Natural or artificial, random or designed, accident or message. We don't know, and that's okay. Uncomfortable, yes. Frustrating, absolutely. But okay. Because not knowing means there's still mystery in the universe. Still. Things that resist easy answers. Still wonder. A philosopher writes an essay in early November. Title, The Gift of Uncertainty, What 3i Atlas Teaches Us About Knowledge. The core argument is simple. We live in a world that demands certainty, that rewards confidence, that punishes ambiguity. But the universe doesn't care about our demands. The universe is vast and strange and full of things we don't understand, and 3i Atlas is a reminder of that. A reminder that we are small, that our knowledge is incomplete, that there are things out there, objects, phenomena, maybe even intelligences, that we're only beginning to glimpse. And instead of being terrified by that, maybe we should be grateful, because uncertainty means possibility. It means the universe is bigger than our models, richer than our theories, more full of surprise and wonder than we dared imagine. The essay ends with this line. 3i Atlas didn't give us answers. It gave us something better, a reason to keep looking. And people are looking. Not just at 3i Atlas, at everything. Telescope time is being dedicated to searching for other interstellar objects. Surveys are being expanded. Detection algorithms improved. Because if 3i Atlas taught us anything, it's that we weren't looking hard enough. We were seeing these objects and calling them asteroids, comets, natural debris. We were filtering them out as noise because they didn't fit our expectations. But now? Now we're paying attention. Every object that moves a little too fast, reflects light a little too strangely, shows a feature that's a little too precise, gets flagged, studied, considered, and maybe, probably, most of them will be natural. Weird, but natural. But some might be like 3i Atlas, ambiguous, provocative, impossible to ignore. And each one will add to the picture. Each one will help us understand whether we're seeing a pattern or an anomaly, whether the galaxy is full of these objects, or whether 3i Atlas is unique, one of a kind, a singular mystery that happened to pass through our neighborhood and leave us forever changed. On November 10th, a journalist asks an astronomer, "Do you think we'll ever know what 3i Atlas really was?" The astronomer pauses, looks up at the sky. "I think we already know as much as we're going to, and that has to be enough." Does it bother you, not knowing? Yes, every day. But it also excites me. Why? Because it means the universe still has secrets, and as long as there are secrets, there's a reason to keep searching. That's the legacy of 3i Atlas. Not answers, but questions. Not closure, but openness. Not certainty, but wonder. It arrived in our solar system, silent and strange. We saw it, studied it, argued about it, and then it left, as mysteriously as it came, and we're left standing here, holding photographs of something we cannot name, looking up at a sky that suddenly feels less empty, not because we found proof of alien life, but because we found proof that the universe is full of things we don't understand yet, things that challenge us, provoke us, invite us to look harder, think deeper, imagine bigger. As November continues, 3i Atlas grows fainter. 14th magnitude, 15th, 16th, slipping below the threshold of amateur telescopes. Soon only the largest professional observatories will be able to see it. And then by summer, nothing. Just data, archives, memories, and one question that will linger long after the object is gone. Did we just see proof of intelligence beyond Earth? Or are we seeing patterns in the void because we are desperate not to be alone? The honest answer? We don't know. We may never know. And that's both terrifying and beautiful. Because the question itself, the fact that we can ask it seriously, based on real evidence and real observations, means something has shifted. The universe is no longer a place we fully understand. It's a place full of mystery, full of objects we can't explain, full of possibilities we're only beginning to consider. And maybe that's enough. Maybe the journey is more important than the destination. Maybe the wonder is more valuable than the answer. Maybe 3i Atlas came through our solar system not to give us proof, but to give us permission. Permission to wonder, to question, to look at the universe and say, "I don't know what that is, but I want to find out." The sky does not answer. It never has. It hangs above us, vast and silent, full of light and dark and everything in between. And 3i Atlas moves through it, a single point of light growing dimmer with each passing day. Unconcerned with our debates, our theories, our need for answers, it simply exists, moves, endures, as it has for unimaginable spans of time, as it will continue to do long after we've forgotten about it, drifting through the dark, silent, eternal, unknown. And we stand here on this small blue world, looking up, changed by what we saw, humbled by what we don't know, awed by the vastness of possibility. We saw something. We don't know what it was, but we saw it. And that matters, because seeing is the first step to understanding, and understanding is the first step to knowing our place in this vast, strange, beautiful universe. 3i Atlas is leaving, but the questions it raised, those will stay with us forever. And maybe, just maybe, that's exactly what it was meant to do. Not to give us answers, but to make us ask, to make us wonder, to make us look up at the night sky and see it not as empty, but as full of mystery, full of possibility, full of things we're only beginning to understand. The object does not look back. It never did. But we do. We look up. We wonder. We search. And in that searching, we find ourselves. 3i Atlas continues its journey through the cosmos, fading, silent, eternal. And humanity continues its journey too, forever changed by a brief encounter with something we could not name. The universe keeps its secrets, but we keep searching. And in that search, we find meaning. We find purpose. We find wonder. The sky does not answer, but it invites us to ask, and that is enough.